Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Camera Tuesday, we're going to talk about lens resolution or MTF. So let's dive deep into it. So what is this resolution? Well, first thing you have to understand, if somebody is talking to you and the first thing they are saying is the megapixel, it means nothing. Like, I do not have to prove to you that a 100 megapixel or 108 megapixel mobile phone photo compared to a GFX 100 megapixel, which one would be better? But question becomes, like, scientifically, why? Are they lying or they are doing something magical? Well, the point is, lens is the missing part here. This lens versus this lens, that's the issue. This lens is not sharp enough. And for example, if you are familiar with our mobile phone history, you must have known we had a really high resolution mobile phone sensor surprisingly early. Like, they were like very early on. I remember 48 megapixel before we even had like Androids. So then why the heck we did not have good quality mobile photos? Simply because of the lens. It took quite a long time before our lens technology caught up to the sensor technology. So that is the whole thing you have to understand. Megapixel are not the first thing, they are the last in the line. First in the line is the lens. If lens is not projecting properly, megapixel is just fluff at that point in time. Lens has to take the real, basically this whole scene has to go through my lens first, then it goes to a sensor. That is a very, very critical aspect. Lens has to be the first line of basically defense, so to say. And if the lens is poor, you will not get what we classify as high fidelity. So if any Tom, Dick and Harry says, oh, I have 8K, I have 12K, I have 18K of IMAX, it means nothing. Because whenever somebody is talking in those big numbers, they are talking fluff. Because there is no lens that is high resolution enough. Are there lenses that can be made that resolution? Absolutely. Then who uses those? Military spy satellites and NASA observatory satellites. Yeah, those lenses cost millions of dollars per piece, and each mirror can take upwards of years to grind. And not to mention, lens itself could take millions of dollars. So that's why the fidelity of your sensor means nothing if the lens itself is not high fidelity enough. For example, you can easily see many cameras are like 48 megapixel, but it gets bit slapped by other 12 megapixel mobile phone. How? I can guarantee you, if that's happening, it's because of the quality of the optics. The lens was high resolution in 12 megapixel, and in 48 megapixel, it's just fluff. So this is a very, very critical aspect. And real world has infinite resolution. So let that be very clear. Same way in audio signal, it has infinite continuous signal. Same way in basically scene, you are seeing, you can have infinite resolution here also. Meaning, if you had a magical lens, let's say alien technology lens, you should be able to zoom in one corner. You should be able to zoom in into sub a pixel. But real world is a bit more limiting, so to say. So infinite resolution gets squashed down by the lens itself. And our sensor technology and lens technology has to work with each other. And that's the reason why early days we did not have like super duper hyper high megapixel cameras. Could we have built it? Yes. Would it have been expensive? Yes. But they're expensive today also. So it's just, why didn't we? Lens were not good enough. Once we actually jumped into digital era, we actually started to analyze corner to corner, pixel peeping. Then people are like, lens is just not good enough. It took lens engineering quite a while to catch up to a point where they can, okay, now I can actually render 20 megapixel. So that is the primary reason. If any Tom, Dick and Harry talks to you is like, this Blackmagic cinema camera has 12K, it has nothing. Do you have a lens that can render 12K? Most of the cinema grade lenses, most of the broadcasting lens, no. Full HD or 4K, that's it. So real world has infinite, lens has to compact it down, and how the heck it's compacting it down, that defines how much resolution you get from your sensor. Sensor is the easy part, ironically so nowadays. So lens is the part that has to be done properly. So how do we quantify it? Like, it's one thing to say, oh, this lens is happening. Like, how the heck do you quantify it? So for that, engineers came up with this ingenious idea of MTF. What it is an industry standard. That's how every other lens manufacturer compares themselves to an objective measurement. Now, this measurement does nothing with color. Let that be very clear. It can tell you contrast, it can tell you resolution, but it cannot tell you color. So you may find yourself in an odd situation where you may like color rendition of a lens which may not be sharp enough. So be mindful, MTF only tells you resolution and sharp, basically contrast. So how the heck it tells you, physically tells you that this is what it is? Well, it generally goes into the basics of data. That is a signal. What is a signal? something is changing. That's a signal. So you take a line, as in a black bar, and then you put white bar next to it and make sure the edge is as sharp as possible. So within reason, now you have a line pair. You have white and black. Basically, that is a square wave signal. So once you have square wave signal, you send it through your lens and then you study it in your sensor. And sensor will never able to transfer 100%. Why? Glass is not 100% transparent. So if you are getting 100% in and 100% out, something is wrong. So glass will dull it down a bit. Now how it will dull it down? A square wave signal, basically a pixel going from white, black, black to white, gray, then black. So there will be a transition zone. How sloppy that transition is, that curves your signal. That is what we call loss of contrast. So you started with 100% contrast, your lens will lose some percent of it. For example, it could lose 10% of it and then you have 90%. And that's actually a good result. So this is how we scientifically can say this lens is contrasty or this is not contrasty. Then you increase the frequency of that signal. So instead of having big chunky lines, you make the lines smaller. So instead of, like, let's say having 10 lines per millimeter, you could have 30 lines per millimeter. At that point in time, the signal is still square wave, but transfer is not happening. That means resolution is not going. So at that point in time, your contrast loss will tell you. And if you try to make lines even smaller, you will only get gray. Even though signal is there, all you are getting is gray blob. What does that mean? That simply means it is no longer resolved. You have reached maximum resolution. So having a sensor that can dissolve at that point, like, oh, I can tell you A from B. It's like, dude, there is no point because lens is making it blurry. Sensor will not help you at that point. So that's how we tell this is sharp or this is blurry. Like from if you look into Nikon, this is how they, and be mindful, lenses are always spherical, as in like their projection area is round. They always take diagonal of the sensor. So you will start from center and then you go to the corner, and that's why MTF charts are always going like this. If they're directly showed from both sides, it will look like a bell curve, which would be redundant. So people come up with the idea from center to edge. That's it. And edge is always diagonal like this because it has to go to the final corner of the pixels. So we use generally bare minimum two dataset. Dataset one is 30 lines, dataset another is 10 lines. So whenever you are trying to take a photo, your charts and all that, it will have one 10 line pairs per millimeter and 30 line pairs per millimeter. One helps you figure out the contrast, another helps you to figure out the resolution. Basically, if you want to capture doggies, let's say you are working with a lot of doggies and puppies have very high density hair on them. So at that point in time, you need a lens that can resolve 30 lines per millimeter quite efficiently. Otherwise, you can put a sensor behind it, like that's 8K or 12K. Output will not be good because that resolving is not happening, because lens is the compacting point. If lens compacts it too much, you will only get a gray blob. So this is a very critical aspect. And mathematically, we utilize 10 lines pair for contrast measurement, because again, there's a big bold. It tells you what is the most optimum contrast transfer you can have. And then you have 30 line pair, which is for spatial resolution. Meaning, you must have heard when we are talking about satellites, we'll say, oh, 5 meters per pixel. Oh, 10 meter per pixel, as in the spatial resolution is low. And sometimes you could be like, it's 1 meter per pixel. That would be God tier spy satellite, which there are, but thankfully we have atmosphere that is shimmering. So even though it mathematically can resolve it, Earth's atmosphere is like, nah, bro. So this would be high spatial resolution and this would be low spatial resolution. To figure out our spatial resolution, we utilize 30 lines. Be mindful, this is not necessary, that's it. You can go to 40 lines, 50 lines. If you want to make a telescope and you are commissioned by NASA or something like that, they will be like, bro, 30 is starting, we go to 300 lines per millimeter. You want to be that sharp. And all the data, be mindful, this data, because it has to take care of all the lenses that has been made and all the lenses that could be made, the data here is relative, meaning it tells you from 0 to 100% and from center to edge. That's all. So you can actually cross compare. For example, if you are trying to test a lens, two prime lenses, and let's say their millimeter is not perfectly lining up. Let's say one is 100 millimeter, another is 135. But you need sharpness. That's your goal. Like, I need sharpness. You can still utilize this. If framing is flexible, you can look into sharpness as a deciding factor. Meaning, let's say two Sony lenses are available and you're like, you know what, both will do more or less what I want to do, but I want the sharpest lens available. And even if the prices are very close to each other, use the MTF chart and voila, you know which one is mathematically sharpest. So this is how we built the MTF module transfer function, meaning how much you actually transported. And this only tells you contrast and resolution, meaning how fine of a detail of real world can actually transfer, and how much contrast can be preserved. It will never be 100%. So if you see a graph that starts at 100%, generally either it's very low resolution graph or somebody messed up. So be very mindful. And as you increase from, like, let's say 10 would be close to the upper end. 30 lines, it will go down a little bit percentage wise, and 50 line, it will go even lower. Higher the resolution requirement, the uglier lens becomes. So that's why you cannot just, oh, I had a lens, now I'm gonna upgrade the body from, let's say, 24 megapixel to 60 megapixel. You're not going to get 60 megapixel. Most of people experience that, but why? It's not the problem of the sensor, it's the problem or limitation of the lens. If they had a truly high quality lens, for example, Sony G Master lenses, Sony's claim is that they target it for 100 megapixel sensors. That meaning that internally they are testing it for much higher basically fidelity. So in future, if they release a 100 megapixel sensor, the camera lenses that are G Master class, hopefully they can resolve it. And that's the whole point why they have a G and G Master. G is rated for much lower than that. But realistically, only 1 or 2 modern G Masters are actually that good where I can trust it. But previous Mark 1 basically G Masters were not that good. But that's what companies were aiming. And same is something similar is going with Canon also, where they will have Canon lenses and Canon red ring lenses. The red ring was designed for much higher resolving power. Because remember, this thing is very easy to, and why contrast matter? Because reading this is easy, reading is hard. Why? Contrast. Resolution is exactly the same. Be mindful, the size is exactly the same. The spatial resolution is exactly the same between these two, but one is super easy to read, another is super hard. Why? Contrast. The black and white is not going black and white, it's going a little bit black, it's going a little bit gray. So that means the contrast is sloppy. If you have sloppy contrast, output equals garbage. That's why we only measure sharpness using contrast, resolution using contrast. Once we have that, then only go, okay, this is the resolution and this is the contrast. It does not do anything with color. Let that be very clear. Color is the one thing that MTF cannot tell you. So what about the charts, so to say, this chart? This chart is super simple. All you have to understand, vertical axis is percentage, basically how much you are transferring from real world to your sensor, basically the projection efficiency. So 1 would be 100%, 0 would be what the hell. So 1, awesome. 0.9, super awesome. 0.8, that's actually good lenses. 0.6 to 7, that's the point where most of your lenses would be. Generally, if you just go ahead and buy the lens, or most likely look into your lens, most kit lenses would be as low as like 0.5 of transfer to 0.7. This would be the zone. A quality lens would be from 0.6 to 0.8. Super quality lenses would be like this. Like this lens is, I do not even know, Mark 3 or Mark 4 from Sony's internal. And this time they just went all in. They were like, Da shall have a high resolution lens, which actually justifies the G Master tag. It is 135mm f1.8 G Master, and the chart is transferring almost 80%. And be mindful, I have specified there are generally 2 pairs. You have 10 lines and 30 lines, right? That's the bare minimum, that's the standard. Be mindful, that's bare minimum. What if you go above that? What if you go from, let's say, 10 line pairs, 20 line pairs, 30 line pairs, 40 line pairs, and 50 line pair? This freaking thing at 50 line pairs can transfer 80%. Most lenses do not do 80% at even 10. Like 10 they do nowadays. 10 should be doable, but at 30 is like drops drastically. So having that sort of sharp resolution, meaning if this lens is put into a high resolution Sony body, you'll be like, no, I'm like, my 60 megapixel is 60 megapixel, because this puppy is like, I got you, fam. If you put a lens that, let's say, just 50 lines line pair resolution is from here, you can put whatever the hell lens you want sensor on it. It won't resolve much. So this is the whole point. Percent transfer and from center to edge, and you can see it will always fall off. Now it is because our engineering is so good that fall off at big chunky details is almost negligible. So if you are capturing something big, resolution fall off would be very minimal. But if you are trying to capture something that is intricate, let's say you want to photograph a diamond ring using a macro lens, people would urge you to still put it in center. Reason is that at high resolution, basically you have a lot of fidelity in the scene, you do not want to have that fall off. And be mindful, the higher the resolution, the faster the fall off happens. So for that reason, if you are trying to capture a macro of something detailed, do not go rule of third. Crop that in post, but do not do it in capture. because the lens is the limiting factor. And this is how the lines are designed, from center to edge. So this is the axis that tells you how much transfer happened in terms of percentage. This from 0 to 25 millimeter is the edge part. So this gives you two axes in the graph. Now, what is this lines? I'm telling you percentage, but what about the lines? What does that line mean? That line simply means basically Skegitalian line. I have no idea. Okay, I'm gonna call it mathematically what it is. Parallel to axis, meaning if you take the lens and you have a spin around it, that's, and you have parallel drawings to it, line parallelly to it, that's classified as parallel lines. And then you have meridian, that is perpendicular. So you have parallel lines and perpendicular lines. That's all you have to worry about, parallel and perpendicular. So this is the lens, this is a line, and if you are parallel to it, that's one data point. If you are perpendicular to it, that's another data point. That's all there is to it. Now question becomes, why you have two? I'm not talking about the fidelity, as in it's not, both could be 10, both could be 20, both could be 30, both could be 50. But then why do you have to have this two data point? Why each of these lines always have a single line and a dotted line? Why? Well, because we realized very early on that lenses have schematism. Basically, astigmatism is there in most lenses, and it is the nature of reality itself. It will be there. So having these two lines, horizontal, parallel and perpendicular, helps you to figure out how bad it is. So that's why ideally in ideal lens, both of the lines would be as close to zero as possible, as in like deviation between these two lines you want to be as little as possible. But realistically it's not going to happen, especially at high resolution. It starts to fragment out. Because of this, you have transitional astigmatism, and basically it's the optical axis is not perfectly aligned. This happens. Of course, these are extreme examples, but all lenses have that. That's why you have these two data points. And if you have those two lines as close to each other as possible, that means the micro contrast would be awesome. Meaning you look at lens, you're like, that's a good lens. So we use 10 line pairs per millimeter for contrast representation, is like how contrasty is the lens, and then 30 lines per millimeter for resolution. Now we do not stop at 30, that's not necessary. It's just a standard that we started from negative era, so 30 were like more than good enough. Now in digital era we need to go further than that, but it's not done that everywhere. But this data set that I'm showing you came from a lens rental site, and from their point of view it kind of makes sense that if you are actually buying a lot of lenses, renting them out, it would be much better to just invest into one of equipment. Those equipments are expensive, and just do the testing yourself. So when you say, okay, this lens is sharp, you know it is sharp. If you buy 10 from Sony and one of them is not performing, you know that lens is defective, rather than, oh, you know, it's not, the lens is lens, it is. No. So this data is from them, and they did a really good job of, like, you know, actually going 40 lines pair and 50 line pair. And this simply means 135 millimeters genuinely good, like good. And you can see the line remains very close to each other. So micro contrast would be also useful, and especially if you're not talking about something very high spatial resolution in scene wise, you will have awesome, because see, red line is almost just one line. That's awesome. So 10 is the bare minimum, 30 is the resolution one. You can go further than that, but you will always have two lines, because one would be parallel, another would be perpendicular. That would be the two line. The closer they are, the better the micro contrast rendition would be. And higher ppms can be used. Basically, line pair should be used if you want very high resolution. If you're like, hey, I want to use medium format camera, if you're paying that much money on the lenses, you really should look for something more than this. Like 50 would be like bare minimum at that. It's like, bro, go below that. And be mindful, people do. Like, if you ever wondered why the heck telescope lenses cost so much, that's the reason. They are tested to even higher than this. So this is how we study the charge. Percentage, center to edge, and the line, the closer they are, the line are to each other, the better the micro contrast. The flatter the line, the better from, like, you know, resolution, sharpness, corner to corner sharpness would be better. And the fall off will happen if you increase the resolution, corner, as in like the fidelity of the scene. If you want to capture, please focus on the center. Like, yes, it's unfortunate that we have not solved it, but the only way to solve it physics wise is using mirrors, not lenses, because mirrors are first incident surface. So that's how James Webb Space Telescope do. But if you have that kind of budget, you would not be watching this video. So this is how you study the chart part. So what's the use of it? That's the chart. Let's say you understood it. What's the use of it? Well, lens is the first part. first part of your optics. That's why I said, like, if you're like, oh, Blackmagic has 12K, that's the highest resolution, it would be garbage compared to RE's 65 that is not even 8K. Why? Because it's huge and they know for a fact that lens can only resolve that much. So they are focusing more on color rendition rather than going YOLO on like megapixel. They're like, that's the whole point. You can have 8K in like your point and shoot, but does it have enough lens power to resolve 8K? No. So that's why low megapixel with high MTF lens always will give you better results compared to high megapixel with poor MTF. Be very mindful, and that's the primary reason why 100 megapixel in a mobile phone does not mean anything, while 100 megapixel in a medium format where they have a lens that is actually matched to it, you'll be like, damn. So this is the whole point. And unfortunately, there is no international standard like how we have CPA rating for batteries. We do not have any international standard for MTF charts. So unfortunately, companies have diverged to a point where they are not cross compatible, meaning if you look at a Canon chart, you look at a Sony chart, they are not cross compatible. Like, why? Even though both of them will say this is the red line would be generally, the flatter line would be the 10 lines per pair, and the line that has curvy generally would be 30. Same would be here, Canon also. But other than that, how they are actually conducting it, what tools they are using, what projection method they are using, those things are fluffy. Consequence of that is, if you want to compare Canon, compare it to other Canon. Meaning, let's say Canon released 5 or 6 lenses, and you are like, hey, you know what, framing, I'm comfortable. But these two lenses, let's say 100mm and 135mm, they are close to each other in terms of cost. And the only requirement you have rather than framing is the sharpness. Look into MTF. Canon to Canon MTF will work. Sony to Sony MTF will work. Nikon to Nikon MTF will work. So this is how you use it. Do not jump from brand to brand. You cannot be like, okay, I'm going from Sigma to Tamron to Canon. No, that cannot be done. Unless it's a third-party chart. Back in the days, we had the ExoMark company that was doing that, but they went bankrupt because there is no actual valid way of monetizing this data. So I do see it, but I really wish somebody start to do this again. Because there is no point of having, I have 60 megapixel. It's like, do you have a lens that can resolve that? Because this is the only lens, Sony lens, that I would trust with 60 megapixel, and this is the only high megapixel lens that I would trust with 50 megapixel, 135, 105. And be mindful, the wider lenses are always blurrier. Like, if you want sharpness, do not go with wide lenses. Like, it's the law of engineering and physics. And zoom lenses will always be worse, and they will always have worst fall off. Meaning they will start here, damn. It will always happen. Because the testing methodology is not fixed, you cannot jump from Nikon, Canon and Sony. Third party will help you to cross check. So if you are like, hey, I'm thinking about Sigma and I'm thinking about Tamron, and if you need factual data, it's like, bro, I can solve the color, but I cannot solve blurry image. Because blurry image, once it goes there, you cannot increase sharpness in Lightroom. You cannot do anything to it. If you captured a ugly image, a blurry image, it's blurry image. If you have to capture high contrasty and high resolution image, only then you can tamper with color to some extent. So these things you have to understand very thoroughly. Now, that being said, talking from scientific point of view, this is half of the equation. Meaning, whenever you are talking about photography, you're not talking about scientific things. You're not talking about espionage. You're talking about feel, meaning science plus art. So MTF takes care of the science part, but you may have a scenario where like lens is too sharp. For example, many people have complained about this lens, it's too sharp. And like, how the heck that's possible? Well, it is possible. If you watched any of the older TV show, many of them you also, if they wanted to show ethereal feeling, whereas like, girls are too pretty, they will have Vaseline on top of the lenses. I'm not joking, this was actually done. And again, even in modern times, we do the same thing, only instead of putting Vaseline, we have a glass which we call glimmer glass. It makes the lens infinitely blurry comparatively. Like, by design, it makes it blurry. But why? Again, if you are shooting a romantic movie, that's what you want. Like, if you take this lens, is sharpest apparently in the Sony lineup, you take this lens, put it the sharpest sensor, as in let's say 60 megapixel sensor, you take a girl's photo, like, she might fire slippers at your ass. You do not want to give someone where you can say, hey, dude, I can see brush strokes. You do not want that. And again, that's why professional model, basically makeup artists cost so much. They actually make sure that brush lines are not visible in the face. I did not even knew that. Like, makeup artist price goes up by case. Oh, full HD makeup artist, this kind of price. 4K makeup artist, this kind of price. IMAX party, this kind of price. I did not knew this, but it is. And it does make sense why the heck actors and actresses, when they are going with like top quality movie, they actually spend hours for makeup. It has to be done, it has to be blended, everything has to be done. Otherwise in 200-inch display you'll be like, hey, I can see paint marks. You can see that. So be mindful. MTF is good to know, awesome to understand, but it's half of the equation. You may be like, hey, this is a blurry lens, but I love the rendition. That's up to you. Heck, like I have this puppy, so let that be very clear. Lens MTF is lens MTF. It's one way of comparing the sharpness, but if you're talking about basically feel of the lens, that's the other half. And if you like the feeling of the blurry lens, go with blurry lens. Is the feel. That's what sells. So be very mindful. So this was my presentation on basically lens MTF, lens resolution. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.